Hey class, I wanted to make a video here for this problem on the workshop. We got this interesting setup where we have these three different blocks, a 6 kilogram block that's tied to a 4 kilogram block, which then is tied to a 9 kilogram block that's hanging off the back of this ramp here. And we're given the masses, that's it, and then asked to find the acceleration of the system. And we're told that it accelerates, the 9 kilogram block accelerates down, while the 4 and 6 kilogram blocks will accelerate up the ramp. And we're asked to find that acceleration. So it's interesting because we really don't know much. All we know are the masses and the coefficient of friction between the ramp and the 6 and 4 kilogram block, and that's it. So there's two ways to go about solving this. One is to look at each block individually, drawing a free body diagram for each block individually, and then doing some of the forces, combining those to solve. That's the most general generic path, and so I'm going to show you that first. But you can also treat the system as a whole, looking at just the net external forces on the system in the direction of motion, and you'd get to the exact same results, similar to how I demonstrated in one of my sample video problems. So let's look at this one at a time, starting with the 6 kilogram block. What are the forces acting on this? Well, in the straight downward direction is the weight of the block, so we're going to have mass times gravity, 6 kilogram mass. Perpendicular to the ramp is the normal force, so up here we have the normal force. And in fact, while we're thinking about this, I'm going to go ahead and add some axes here. I like to define the positive x-axis in the direction of motion, so I'm going to call positive x up the ramp, and so therefore positive y is perpendicular to the ramp. So, okay, we got the normal force, we got the weight, and then we also have the string here that's pulling it attached to the 4 kilogram, this guy here. I'm going to call that T1, and then I'm going to call the other string T2. So pulling up the ramp is T1, and then going against the direction of motion is the force of kinetic friction. Now if we move on to block number, or the 4 kilogram block, the second one here, again, I'm going to draw some axes. Oh, that's terrible. Let's redo that. Parallel and perpendicular to the ramp. And so now if we look at the 4 kilogram block, it's going to look similar in many ways. It has the weight going straight down. It has tension 2 pulling it up. It has the normal force perpendicular to the ramp. It has T1, which is pulling backwards on it, and also going backwards in the negative x direction is the force of kinetic friction for the 4 kilogram block. Okay, good. Also, just a quick side note or reminder, we proved this with geometry, but the angle between the negative y-axis when we rotate our axes like this and the weight force is the same as the angle of the ramp. So in both cases, these here are the angles of the ramp. And then when we come over to the 9 kilogram block, now we can actually keep our axes just straight up and down, horizontal and vertical. And for it, the free body diagram is much simpler. It's got the weight going straight down, and we have the T2 pulling up. If you're curious about my sloppy little subscripts, I'm just putting a 4, 6, or 9 as the subscript on the mass to help me distinguish which block I'm talking about. So from here now, our general process is always to write out some of the forces, looking in the vertical and horizontal directions, or the x and y directions. So if I started with the 6 kilogram block, and I wanted to do some of the forces in the x direction, I know it's going to be equal to mass times acceleration, since it's accelerating up the ramp. So I just take and add up any forces in that direction. So in the positive x direction, I have T1 positive. In the negative x direction, I have minus the force of kinetic friction for the 6 kilogram block. And then also in the negative x direction, I have a component of my weight force. There's a component of the weight force going down the ramp, as is there a component of the weight force into the ramp. So I also have Wx, which we've seen now a couple times is equal to the weight times the sine of the angle of the ramp. So in this case it would be m, the 6 kilogram m, times g, times the sine of our angle theta. Those things all then are going to be equal to m, the 6 kilogram mass, times a, its acceleration. Now if you recall, force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So in order to substitute in here, we need to find the coefficient of kinetic friction as well as the normal force. The coefficient of kinetic friction is given, so that's just a value that we have. And the normal force then, we have to look at the y direction to find the normal force. So if we do sum of the forces in the y direction, you would set those equal to 0 since it's not accelerating in the y direction. And what you would get then is you have the normal force going up minus the y component of the weight, which is mg cosine theta equals 0. So solving for the normal force, you can see the normal force is equal to mg cosine theta. And so now we can plug in for the force of kinetic friction. So sliding up just a little bit, I'm going to rewrite my sum of the forces equation again. T1 minus the coefficient of kinetic friction times the weight times the cosine of theta. That's all just the normal force. And then minus mg sine theta. That's again just keeping this term here. And all of that equals ma. Oh boy howdy, that's a lot, and that's just one equation. You have to do the same thing for the 4 kilogram and the 6 kilogram masses. Now I'm going to let you practice going through the step-by-step process for each of those, but so you can check your work, when you do the 4 kilogram block, what you should get is an equation that looks like this. T2, which was in the positive, minus T1, minus the force of kinetic friction, which ends up being mu times mg cosine theta, similar to what we saw before, and then minus the x component of the weight, which is mg sine theta, and that all is equal to ma. And then when you do the 9 kilogram mass, what you're going to get is T2 minus mg equals m, but check this out, times negative a, because it's accelerating down and we're calling up the positive direction. So you have to be super careful to include that negative sign. So from here, in order to solve, you need to combine these all into one equation, so it gets ugly. But if you solve this for T2 and plug it in up here, solve this for T1 and plug it in down here, you can combine these into a single equation that enables you to solve for A. And that single equation is the same that you would get if you dealt with the system as a whole. So just to show you quickly or briefly here how to deal with the system as a whole, okay, if we redraw our pictures here, looking at just our blocks, this is kind of our setup, right? If we define axes now in terms of the direction of motion, being here for these two blocks and straight down for this guy, and then perpendicular to those, can be the alternate axis. Keeping in mind, again, we have these blocks moving up and this block moving down. Then you can think about forces acting external to the system. So what we have external to our system is we have the weight of this guy going down. We have the weight of these two. We have friction on each of these two. And then we have the normal forces. Oops. And those are all of our external forces. So what happens then is if we try to do sum of the forces on our entire system, it's going to be equal to mass of the entire system times the acceleration of the entire system, but we're going to do this in the direction of motion. So basically I'm defining along that red, the first red line, let me kind of show you, maybe I'll show you in yellow. I'm defining anything going this way as being positive and then going against that as being negative. So if we look, there's actually only one force that's positive in that direction, and that's the weight of the 9 kilogram mass. Everything else is in the negative direction. So we'd have minus the force of kinetic friction on the 6 kilogram block, minus the force of kinetic friction on the 4 kilogram block, minus the x component of weight for the 6 kilogram block, and minus the x component of weight for the 4 kilogram block. Again, you have to substitute in for these coefficients, or for these forces of kinetic friction like we did last time, but those are all of the forces in this direction, and that equals the mass of the system. So that's all the masses added together times A. And so since these are all values you know, you can solve for the acceleration. So I hope that helps you get started on this one. Give it a go, and hopefully you get a box-worthy answer at the end.